Assalamu alaikum everyone, this is Sumaya. I'm going to talk about zero liquid discharge system. As everyone knows, freshwater scarcity is considered as one of the most critical global challenges of our time, poses a major threat to economic growth, water scarcity, and ecosystem health. Zero liquid discharge is an engineering approach and an ambitious wastewater management strategy that eliminates any liquid waste leaving the plant or facility boundary, with the majority of water being recovered for reuse. Achieving zero liquid discharge, however, is characterized by intensive use of energy and high cost. As a result of zero liquid discharge has long been considered not viable and has been applied only in limited cases. Zero liquid discharge processes makes effective use of wastewater treatment, recycling, and reuse, thereby contributing to water conservation through reduced intake of fresh water. Worldwide construction of zero liquid discharge plants represents an average of $200 million US. Moving on to the drivers, benefits, and challenges of zero liquid discharge, the main drivers of zero liquid discharge implementation are water scarcity, water economics, and environmental regulations. Water scarcity intensifies globally. The capability of zero liquid discharge to recover water to the largest extent further enhances its prospects. Stricter regulations for wastewater disposal are the primary driver for zero liquid discharge. More costly non-compliance penalties along with increasing costs of wastewater disposal can overcome the high expenses of zero liquid discharge installation. Regarding to the benefits, the organization's factor to target zero liquid discharge, achieving it is very efficient economically, which aim to decrease the cost of zero liquid discharge operation, promote sustainability of the industry and the environment at large. While the main challenges are the need of integration of suitable technologies to achieve reduce, recycle, recovery, and reuse. Furthermore, capital cost and operating costs of zero liquid discharge, including energy costs and chemical costs associated with the evaporation and treatment processes, are considered very way higher than any other disposal techniques. Finally, effluent composition and characteristics and material compatibility are also considered some of the zero liquid discharge challenges. Zero liquid discharge thermal system. In this figure, we can see that the major elements involved in this system include wastewater pre-treatment, treatment in a brine concentrator and brine crystallizer, followed by evaporation and solids recovery. During pre-treatment, wastewater undergoes various processes such as filtration, pH adjustment, deaeration, and anti-scaling to minimize the scaling potential of water. Next, this water is sequentially concentrated using brine concentrator followed by brine crystallizer. This produces distillates that are recycled and reused as clean water, while solids are either recovered as valuable byproducts or sent to evaporation ponds for disposal after further processing. Reverse osmosis and emerging membrane-based zero liquid discharge systems. Limitations: brine crystallizers or evaporation ponds are still indispensable for zero liquid discharge processes. Therefore, the focus for zero liquid discharge technology have been on reducing the volume of concentrated brine entering the brine crystallizer or evaporation ponds. Reverse osmosis as well-established pressure-driven desalination technology with excellent energy efficiency compared to thermal desalination, has incorporated into zero liquid discharge operation to lower energy consumption, Unlike thermal processes, reverse osmosis does not require product water to undergo phase transition to achieve separation, thereby eliminating irreversible losses associated with evaporation and condensation in thermal processes. Three membrane-based processes, electrodialysis, membrane distillation, and forward osmosis, emerge as alternative zero liquid discharge technologies to brine concentrators to further concentrate the wastewater after the reverse osmosis stage. The produced brine from these processes serves as a feed to the crystallizer or evaporation pond. Electrodialysis apply an electric potential as the driving force to remove dissolved ion through ion exchange membranes. Membrane distillation is a thermal membrane-based desalination process in which a partial vapor pressure difference drives water vapor across hydrophonic microporous membrane. Forward osmosis, unlike hydraulic pressure-driven reverse osmosis, forward osmosis utilizes an osmotic pressure difference to drive water permeation across semi-permeable membrane. In forward osmosis, water flows from the feedwater to concentrated raw solution with a higher osmotic pressure. This table shows the advantages and limitations for these technologies. For example, the advantage for reverse osmosis is the energy efficiency, while for electrodialysis, forward osmosis, membrane distillation, high salinity limit, and less fouling tendency. For MVC, the advantages are technical maturity and high salinity limit. The limitations for reverse osmosis are the limited salinity range and the high fouling tendency. For electrodialysis, the limitation is a high energy consumption for high quality water product. The limitations for forward osmosis, the low flux at high salinity, and the limited use. Also, the limitation for membrane distillation are low flux and recovery and the requirement for post-treatment. Finally, the limitations for MVC process are high consumption of energy and high operating and maintenance and capital costs. The main environmental and operating characteristics of zero liquid discharge. Despite the main goal of zero liquid discharge to reduce water pollution and to improve water sustainability, application of zero liquid discharge also results in unintended environmental impacts. One risk stems from the produced solid waste. For example, solid waste stored in evaporation ponds have raised concerns about their odors, potential negative impact on wildlife, and risk of the leakage. Similarly, solid waste disposed in landfills may result in leaching of chemicals into groundwater. As discussed earlier, zero liquid discharge consumes large amounts of energy, leading to significant emission of greenhouse gases. Some pretreatment methods, such as acidification followed by degasification, release CO2 from the feedwater into the atmosphere. For example, the application of electrodialysis in concentrating reverse osmosis brine increases CO2 emissions via both energy consumption and decarbonation of scaling control. Also, incorporating technologies with higher energy efficiency, such as reverse osmosis, will significantly reduce gas emission. In addition, emerging zero liquid discharge technologies that can utilize low-grade or renewable energy, such as waste heat, solar energy, geothermal energy, enable further reduction of greenhouse gases footprint of zero liquid discharge system. This slide gives an overview of the factors affecting desalination and future research strategies and directions to meet the challenges that is facing the worldwide application of this process. These 5 areas affect the costs of desalination, and research and development in these areas can be used as cost-cutting measures. There has been extensive amount of research and development work in 4 areas. The 3 areas that seriously require research and development work are feedwater and system characterization, process optimization, and concentrate recovery handling. The advancement in feed and system characterization is a prerequisite for the advancement in the other 2 areas and would automatically benefit the other 2 areas. Efforts should be directed to establishing proper techniques for feedwater characterization and developing of indices for colloidal fouling and for inorganic fouling and incorporating the interactive and hydrodynamic effects that are usually ignored. Advances in computational techniques and coupling the theoretical principles with advanced experimental analysis certainly would provide that opportunity. As mentioned before, once the proper feed characterization method is developed, it would facilitate process optimization for operation as well as for product quality and for concentrate management. Finally, we would like to thank Camp Center and Prof. Said Zaidi for the great opportunity to observe and undergo various desalination technologies. We would also like to thank Engineer Halima for giving us necessary advices and guidance. Thank you.